Hello everyone, hope you are doing well. Welcome to the online platform Civil Technobricks. Guys, here we will tune for instantaneous decoding of conceptual knowledge in the field of civil engineering, where study elaborates decoding the earth to build a better world. Today we will learn the core concepts of geohazards in view of civil engineering. What is meant by geohazard or define the geohazard. So in engineering geology, focusing on geohazards and their engineering importance. That geohazards are natural geological processes that can create danger for human life and engineering structures. Here we are discussing how geological mechanisms influence dams, tunnels, foundations and underground construction activities. So rock deformation, which is a main process which is divided into three stages from stress to deformation to hazard. So stage 1, where stresses are impacted or concentrated on that rock, that forces are maybe tensile or maybe compressive. With respect to that forces, the whole existing isolated rock may get deformed with respect to their folding and strain activity, which is showing the deformation in the middle. And at the end, the stage 3 is the hazard, where the actual structural failure or threat occurred. So a geohazard is a geological state representing a threat to human life or property. It is the intersection of structural geology and civil civilization. So the role of groundwater seepage, which also a main important point, fault zone and rock instability in engineering failure is also a big threat. Here we are explaining the importance of reinforced concrete, rock bolts and shotcrete lining in hazard mitigation. Now mentioning that understanding tectonics or the plates and rock mechanics, which helps engineers to predict the ground failure. Engineering geology connects geological science with practical safety measures in civil engineering projects. The concept of geohazards as a geological event capable of causing structural damage and creating the risk. So the three stages shown in the slides, stress, deformation and hazard formation, discusses how compressive and tension forces acts on rocks within the earth crust. Then the continuous stress leads to folding, strain and deformation in the rock structure in the middle, and at the last, which describes how excessive deformation finally results in the structural failure and geological hazards. Mentioning or explaining the billions of definition that structural geology studies the architecture of rocks formed through deformation. The understanding of rock deformation is most important and essential for identifying future geological hazards. So origin of hazards, it may be a natural or it may be anthropogenic. So natural hazards, the earth's engine, and anthropogenic hazards, human induced. So basically natural and man-made, we can say that. So that geohazards can originate from both natural processes and at the other hand human activities. Natural hazards as processes driven by tectonic movements and earth's internal forces or vibrations, just like natural hazards such as earthquakes, volcanic eruptions and tectonic activities, where anthropogenic hazards as human induced geological disturbances, or we can say that man-made activities, which discusses how engineering interference can disturb or how man-made activities can disturb natural rock equilibrium or stability and trigger instability, just like mentioning the examples such as reservoir induced seismicity, slope failure caused by construction activities and many more. That engineers must understood both natural and human induced hazards for the safe project planning. So endogenic and exogenic forces are in the natural hazards, where engineering interference in the anthropogenic hazards or human induced activities. Classification of geohazards. So we have to classify that geohazards in between the 2 points or two domain, endogenic and exogenic. Endogenic, which is the internal or in between the tectonic plates. Exogenic, which is the external or superficial. Again, endogenic is divided into two parts, volcanic and dystrophic. Volcanic are the central eruptions or due to the fissures, while dystrophic are due to the earthquakes, faulting or folding activities within the earth crust. At the other hand, exogenic is divided into two, mass movements and erosional. Then mass movement includes landslides, rock falls, where erosionals are divided or consist of river incision and coastal erosion. So, with reference to that engineering context, civil engineers must identify the process of origin to design the correct mitigation strategy where geohazards are prevented. So, the broad classification of geohazards into endogenic and exogenic, which is most important point from the planning stage to at the execution stage. The proper classification helps engineers to understand hazard mechanisms and suitable mitigation measure planning. Endogenic hazards like earthquakes and faulting, which introduce the earthquakes and faulting as a major endogenic geological hazards, which explains in three stages shown using the fence example to demonstrate fault movement. Stage 1 describes where the ground and fence remain stable before deformation begins. Stage 2 explains where stress accumulation bends and strains the structure. Stage 3 describes or discusses where rupture occurs causing displacement and fault scrap information. So the seismic rebound explains that which release the stored energy in the form of earthquake, or we can say that vibrations, and which conclude that the understanding of fault behavior which helps engineer to design the earthquake resistant structure. So we have to be aware about the subsurface activity or the portion which is available below to that structure which will be planned, so that the earthquake resistant criteria is designed and the whole structure will be based on that earthquake resistant policy. Fault types and key terms are there. Fault types are strike slip, which is in the horizontal offset, versus deep slip, which is in vertical scrap, just like shown at the image number 2. And key terminologies are focus versus epicenter. So focus is a rupture point, epicenter is a surface point. Focus is a rupture point and epicenter is a surface point. So endogenic hazards, volcanism and collapse. So volcanic hazards introduces and their impact on the geological and engineering environment. Stage A, stage B and stage C. Three stages are there. Stage 1 A, eruption. Stage 2 B, withdrawal. Stage 3 C, collapse. So stage A explains that where magma rises and volcanic eruption begins, which describes how ash columns and lava movement create severe environmental and structural hazards. Stage B explains that where the magma chamber becomes empty after eruption, which discuss how loss of underground support weakens the volcanic structure. And stage 3 describes that where collapse occurs, forming a large depression called as a caldera, which conclude that collapse calderas represent major engineering risk in volcanic regions. So the collapse hazard, which is a rapid eruption drains underlying support, causing massive structural failure of the volcanic cone. This creates collapse calderals, which is a major engineering risk in volcanic zones, just like a caldera collapse. Exogenic hazards, that is a mass movements. That is the mass movements. Mass movement introduces as important exogenic geological hazard, which explains that the slope stability or slope instability may occur due to gravity acting on weak rock masses or weak rock planes or tectonic plates. Tilting discusses an increased slope gradient as major triggering factors. So tilting and increased slope gradient are the major triggering factor which describes how erosion at the toe removes support and destabilizes slope. The role of water and mud also explains the reducing friction and increasing landslide risk. So earthquake mentions as seismic triggers that can suddenly initiate slope failure. Conclude that the rock fragments produced during the slope movement may form megabreccics and cause engineering damage. So megabreccics, just like the landslides, coarse fragments of the rock sides resulting from slide. There are some hanging wall portion is there due to the sliding activity with reference to the detachment fault. So trigger mechanisms: tilting, increased gradient, loss of support, that is the erosion at the toe, lubrication with reference to the water or mud reducing friction, and seismic trigger is that earthquake forces. Geological versus hydrometeorological hazards. So geological hazards with reference to the engineering geology, meteorological hazards or hydrometeorological hazards with reference to the hydrological parameters. So the difference between geological hazards and hydrometeorological hazards, which describes the geological hazards as associated with tectonic plates or volcanic activity, whereas hydrometeorological hazards are the hazards related to the atmospheric and hydrological processes. That groundwater discusses the interaction with volcanic heat may create phreatic explosions. The water available inside the ground may be a crucial for that creating the phreatic explosions. Rapid stream generation or the rapid water flowing inside the earth crust, which explains the explosive pressure beneath the ground surface. That mention the interaction of geological and hydrological system increases overall hazard intensity, just like the earthquake prone areas. Here we conclude that the interdisciplinary understanding is important for effective hazard assessment. So intersection risk is the phreatic explosion, which is interconnected in between geology and hydrogeology, or we can say that meteorology. Most important point, the concept of hazard versus disaster, or we can say that vulnerability. So hazard plus vulnerability is equal to disaster. So hazard is a physical potential where geological event in picture, just like rupture or sliding. Vulnerability where exposure of life and property damage, at the end disaster. So the relationship between hazard, vulnerability and disaster explains that the hazard represents the physical potential of a damaging event. Vulnerability described as the exposure of people, structure and property to risk. That disaster explains that which occurs only when hazards affect vulnerable communities. So it mentioned that an earthquake in an uninhabited area may not become a disaster. The earthquake will cause in uninhabited area may not become a disaster. But when earthquake damages the habitated area, then it become a bigger disaster. So how population density discussed and infrastructure increases disaster impact. So we conclude that the reducing vulnerability is an important part of disaster management. Reducing vulnerability is an important part of disaster management. So a hazard is only a disaster if it intersects with a vulnerable society. An earthquake is an empty result, is a geological phenomenon, not a disaster. So earthquake is not a disaster, but the impact of earthquake is biggest disaster. So how we can calculate the risk? So the risk equation is simple. Risk is equal to hazard into vulnerability. Here we see hazard plus vulnerability is a disaster. Now here we are seeing hazard into vulnerability. We calculate the risk. So risk is dependent on H, that is probability of the event or probability of the hazard, and V, that is the susceptibility of structure based on that vulnerability. So the hazard is often a function of natural frequency and magnitude largely beyond the human control. where the graphical representation shows the recurrence interval in years of probability of event, where on the y-axis magnitude of that earthquake will be there. So lower probability is equal to higher magnitude. Lower probability is equal to higher magnitude. On the other hand, higher probability is equal to lower magnitude. That is the recurrence interval representation. So we can check the probability of hazard event. On the other hand, susceptibility of structure, just like dam or just like any other tunnel or bridge. So dam on shear zone, high vulnerability. Dam on massive granite, low vulnerability. So if we have to mark the site selection for the any type of dam, then we have to mark the site which having massive granite beneath the earth surface, so which gives low vulnerability, so that is low disaster. But if we have shear zone, then there will be a biggest failure or high vulnerability area. So vulnerability depends on exposure, physical resilience and engineering design. With reference to the planning point of view, it is a manageable concept. It is a manageable concept. So based on that engineers goal or engineering point of view, we can say that engineers mitigate risk by reducing vulnerability. Engineers mitigate risk by reducing vulnerability, where site selection and design is most important factor. At the end, the hazard, which is a natural or nature based, is often constant. Moving towards the disaster management cycle, there are four parts: mitigation, preparedness, response, recovery. So, in with reference to the engineering geology point of view, the disaster management cycle used in hazard control and safety planning, which explains the mitigation measures such as hazard zonation and slope stability analysis. Preparedness discuss the activities including monitoring system and seismic networks, which describe the importance of fault mapping and geological investigations. Response explains the activities such as rapid assessment during disasters. Recovery discusses the measures including redesigning engineering codes and rebuilding infrastructure, or we can say the reconstruction activities. And the disaster management concludes, which is a continuous process involving prevention, response and recovery. The role of engineering geology in mitigation, we can say that the geological investigation phenomenon. So rock mechanics as a study of rock strength and deformation behavior. So we have to check the strength of rock and behavior of deformation or settlement. So which explains the importance of determining breaking strength for engineering construction. Here we compare the strong rocks like quartzites with weaker rocks like limestone. So for the construction point of view, we can prefer the quartzites or granite for the strong rocks or for the embankment. Discussing the role of geological investigations in identifying crush zone or low zones of rocks or fault plains, which explain how subsurface exploration helps preventing tunnel collapse and water inflow. Here we mention the engineering solutions such as rock bolting to strengthen the weaker zone of the rock, or we can say that the bolting, which is activity which provide the strong support to the tunnels in the nearby area. We can also use the concrete lining for the same. So conclude that the rock mechanics is essential for designing safe underground structures. So rock mechanics task, subsurface investigation task. So with reference to the subsurface investigation, locating fault plane and shear zones to prevent rock burst or the water inflow activity. So we have to use bolting or concrete lining or shotcreting also for the mitigation technique. Engineering interventions like rock bolting and lining strengthen the weaker zone identified through geological assessment. At the end summary, the summarize that geohazards are geological processes capable of causing structural and environmental damage, which explains the difference between endogenic hazards and exogenic hazards. Here the Here we discuss the importance of geological mapping and rock mechanics in hazard mitigation. The risk equation itself shows that the role of vulnerability in disaster formation. Here we mention the significance of geophysical methods in hazard zonation and site investigation that explain the understanding of faults, earthquakes, volcanism, and landslides, essential for engineers for better infrastructural development. Here we conclude by encouraging students to focus on practical applications of engineering geology in real construction projects. Stay tuned, guys. Happy learning.